What we're going to be doing today during this video lecture is looking at charged objects and the forces between them. And we're going to start to attempt to quantify what that interaction is. So let's get started. Now, here are the things that we already know. These are the things that we have experimented and looked at and deduced. So, we know that things that are similarly charged will repel one another. So if you have two objects that have an excess positive charge, they will repel one another, or if you have two objects that have an excess negative charge, they will also repel one another. We know that things that are differently charged will attract. And differently charged, we said if I have an object with an excess positive charge and an object with an excess negative charge, they will attract. Things that are not charged will attract to things that are charged because of polarization. And remember, we talked about and we looked at and we observed how if I have a charged object and I bring it next to an uncharged object, which we used paper bits mostly as our uncharged object, if we do that, then we see that there is an attraction between them. And we talked about how that attraction occurs because we actually get a shift of negative charges within our uncharged object, which creates the poles in the object, which allows one side of it to attract to my charged object. The more something is charged, the more it will interact. This we saw in our online lab. When we increased the charges of the objects, then the force was much bigger. And we counted the boxes and said that the force was the boxes. The closer two charged objects are to one another, the more they interact. Again, the same thing. As you moved those two charged objects in your online lab closer and closer to one another, you could see that the force got much bigger. So this leads us to, we have all of this information, but what does it mean? So how can we use this information? Well, really what we want to be able to do is to predict some sort of an interaction between two charged objects. And this is really kind of the basis for science, is developing a model from a pattern and being able to use that model to make a prediction about something that will happen in the future. And we could do this by looking at the force between the charged objects. And we already said that that force is dependent on the charge of the objects and the distance between them. We've seen that. But one of the first scientists to do this was a man by the name of Charles Coulomb. And here's a picture of Charles Coulomb. It's like his most famous picture, I think, because it's really the one that you see on most everything. And he was a French scientist. And here's a little bit of information about him. I'm not going to read through it, but you can for sure read through it and look at it. Okay, so I'm going to keep moving forward here. If you want more of this information, you can for sure look him up or keep reading, pause and keep reading. But really, here's what is the important part of it. Between 1785 and 91, he published 7 papers on physics, and they dealt with many different things. But the most important one was the one on forces. And he discussed the inverse square law of forces between two charged particles. And in your online lab, you should have seen this, that you got when the distance between the objects increased and you looked at the force, that you had the inverse square shape. In a later memoir, he showed that the force is also proportional to the product of the charges. And when he put these together, he found a relationship which is now called Coulomb's law. For his work, the unit of electrical charge is now named after him, and he died in 1806. So, how did he do it? What he was doing was he was doing experiments using something called a torsion balance, and the torsion balance was the same way that Cavendish did gravitation experiments to determine forces between masses and the distance between them. But here's essentially what he did. He had a hanging rod with 2 charged spheres on both ends, and then he brought a free sphere that could be charged near them, and he observed the interaction that occurred, and he was able to calculate this force based on the movement of this object. So he charged one of the objects, he then touched it to another one, charging it by conduction. Each of the free moving spheres was then touched to one of the spheres on the rod. He didn't know the actual charge, but he did know that the charges were equal. So he was able to use that ratio to figure out, oh, okay. So he altered the experiment by using spheres of different sizes, and when he used different size spheres, he was able to deduce that those spheres had different ratios of charge based on their volume. He knew that like charges repel, so the torsion balance would twist away, and if he could determine this distance between them, he could figure out how they were moving. And this is a very long and complex process, but he was able to finally come to a conclusion. And his conclusion was that the force between two charged objects is directly proportional to the charge on both objects. So F is proportional to, remember this is the alpha, F is proportional to Q1 times Q2, where we're saying Q is what we're going to use as our symbol for the charge on an object. So the force between the charged objects is proportional to the charge of both objects multiplied by one another. And the force is inverse squared proportional to the distance between the two charged objects. So the force is proportional to 1 over r squared. And remember, we had this very same relationship when we did gravitation, where we said r was the distance between the masses. Now we're saying r is the distance between the centers of the charged objects. And then we get this law. And notice this is very similar to our law of gravitation. Remember, our law of gravitation was F equals g mm over r squared. This is very, very similar, where I have F equals k, which is a constant, which is now known as Coulomb's constant, times charge 1 times charge 2 over the distance between their centers squared. And this constant, this Coulomb's constant, has a value of 9 times 10 to the 9th Newton meter squared per Coulomb squared. F is the magnitude of the force, of course measured in newtons. Q is the charge on one of the objects, measured in coulombs. Q2 is the charge on the other object, also measured in coulombs. And R is the distance between the centers of the charged objects, measured in meters. So, a little bit of a summary of this. Charles Coulomb was a French physicist who discovered that the force between two charged objects depends on two things: the amount of excess charge on the objects and the distance between the two objects, which we've seen both in a qualitative sense and a quantitative sense. You saw that as you brought the tapes closer together, there was a stronger interaction between them. You saw that as you brought the two charges on the online lab together, there was a stronger interaction between them, and you should have a good basis for this. And last part here, the symbol for charge is Q or Q. It could be capital or lowercase, it doesn't matter. The units are coulombs. And a coulomb is a whole lot of charge. One electron, for example, or one proton, for example, has a charge of 1.6 times 10 to the negative 19th coulombs, or 0.00000000000000000000016 coulombs. So a coulomb is a lot of charge. So generally we talk about charge in microcoulombs, and a microcoulomb is 1 times 10 to the negative 6th coulombs. So what you'll find in questions dealing with Coulomb's law is that a lot of times our charge is in microcoulombs, and you have to appropriately convert it to coulombs before you do any multiplication or division or subtraction or addition. The electrostatic force is an inverse square law. In other words, F is proportional to 1 over r squared. And remember, we did a lot of things with these things. As the distance between the objects increases, the force decreases. So if I double the distance, I actually quarter the force. If I half the distance, the force is 4 times bigger. Okay. So in the second video, I will be going through some problems that use Coulomb's law in order to solve them.